announce our second speaker this morning. So it's Dragos Oprea, who is from the University of California, and he's going to be talking about tautological projection for cycles on moduli spaces of abelian varieties.
All right, thank you very much for the invitation to speak at this event, and for the invitation to be in Cambridge for, I've been here for 4 weeks at this point. So I will speak about tautological projection for cycles on AG, and I will report on recent joint work with Sam Canning, Sam Molcho, and Rahul Pandharipande. And we've been thinking about the moduli space of abelian varieties for probably about a year and a half now, and we have some resource to report on. So essentially, my talk will be we'll have two parts, so to speak. The first part, I will have to review some older work of van der Heer, probably like 30 years ago, concerning the tautological ring of the moduli space of abelian varieties. And then in the second part, I will have to tell you some new things. And the new things will be essentially how to decompose a cycle on AG into canonically into two parts, one tautological and another one non-tautological. And to also give you some concrete, to illustrate this by some concrete examples. But let's get started. So as I said, I will spend probably a good, half of the talk by reviewing some older work of van der Heer. So let's actually get started. So the main hero of the talk is the moduli of abelian varieties, but in fact there is a second hero that will reveal itself maybe in the next 10 minutes or so. So let's begin with AG. So AG is, G is a positive integer, and AG, the moduli space of abelian varieties over the complex numbers, appears as a quotient, and what you're quotienting is the Siegel upper half space denoted by HG, and you quotient it by the action of the symplectic group SP2G Z. So just to ground the discussion and make it a little bit more concrete, H plus G is, by definition, the set of all symmetric matrices tau. So tau is a symmetric G by G complex matrix. And for such a matrix, we impose the condition that the imaginary part of tau, if you look at the imaginary part of tau, that's positive definitely. The symplectic group acts in the usual way. So if G is equal to 1, it would act by fractional linear transformations, by Möbius transforms. So if you start with a matrix A, B, C, D, so this is a matrix written in terms of blocks of G by G matrices. So A, B, C, D acts on tau simply by A tau plus B, C tau plus D inverse. So you have to prove, I suppose, that C tau plus D is invertible, but that can be done. So every single tau in here gives rise to a principally polarized abelian variety, which we can denote x sub tau, and this is simply obtained as the quotient of C to the G by a lattice, and the lattice is tau Z to the G plus Z to the G. This is our abelian variety that arises from the choice of tau. So in order to define, so our interest is in the space AG, and this space AG has some nice properties. So for instance, just to familiarize ourselves a little bit with AG, the dimension. So AG has the structure of a smooth stack, but it has dimension G times G plus 1 over 2. So that's something that says something about AG. In order to define the tautological ring that will appear, that will play a role here, I have to tell you a few things about the Hodge bundle. So there is a natural object that we want to consider, and this is the Hodge bundle. It's denoted by E, and it lives over AG. And there are several ways to define it, but here's one way to define it. If you look at the universal, abelian variety xg over ag, you look at the universal xg over ag, and you call this map phi, you can define E simply as being the push forward under pi of the sheaf of 1 forms. So you can look at omega 1 of xg relative to ag and push it forward. So this has rank G, and it has Chern classes, so the rank will be is easily seen to be G. And therefore, we can look at these Chern classes, and the Chern classes are denoted by lambda, so lambda I. This is the ith Chern class of E. And these are well defined, let's say, for I in between 1 and G. So with this understood, I think I could go ahead and introduce van der Heer's tautological ring. And this is simply defined, this is denoted by the letter R, so R upper star. So this will be a ring, it will depend on AG, so this is R upper star of AG. And let's say we work with Q coefficients, so this is generated over Q by the class is lambda 1 dot 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 lambda G. And there are going to be some relations between these classes, so modular relations. So if we are going to speak about the tautological projection, whatever that might mean, we might actually, we would like to actually have a good understanding of this ring. So this ring, you know, if you look at it, you might say, well, it's pretty small. It only takes into account the Hodge bundle. It doesn't take into account perhaps other things that you might want to consider. I'm not gonna speak about this issue at all, like how to extend the ring to make it bigger and more interesting. We'll work with this definition. So I have to say a few words also about compactifications of AG. So maybe I'm certainly not an expert in this, and there's quite a bit to say about compactifications of AG. But let me say a few words nonetheless. So here's something about compactifications. So when thinking about compactifications of AG, there are two types of compactifications you can think about. The first one is the Satake compactification. This is very singular. I'm not going to say it will play no role for us. The second ones are the so-called toroidal compactifications, and those will be relevant for us. So there are infinitely many toroidal compactifications of AG. You can, in order to define them, you have to make some choices. So you have to actually pick an admissible collection of fans in the space of symmetric, bilinear, positive, semi-definite forms with whose radical is defined over the rationals. So there are some choices that are being involved. These choices will play absolutely no role in what I'm going to say, but I would like to say, however, that there are some compactifications that perhaps people have thought about more than others, and those are those so-called perfect cone compactification and the second Voronoi compactification. So unfortunately, I'm not going to define what those are, and you don't really need to know what they are for the purposes of the talk. If when time comes, I will actually say what's important about these compactifications if the situation arises. So in any case, there is a way of extending the Hodge bundle. So one can extend the Hodge bundle A over AG bar, and so you can do that. And if you make your choices correctly, you can even achieve a little bit more from your compactification. So if you pick your collection of admissible fans in a suitable way, you can achieve the following things. You can achieve the fact that AG bar can be chosen to be smooth. Its complement is simple normal crossings. In particular, the perfect cone compactification will not have this property, unfortunately, but for suitable ones, you can achieve the fact that the complement is simple normal crossings. You can also compactify X so that its complement is also simple normal crossings as well. We can describe the Hodge bundle in a very concrete way, namely, if you call pi bar the compactified family, then the Hodge bundle is simply obtained by pushing forward under pi bar the sheaf of relative logarithmic differentials of x bar g over ag bar. What else do I want to say about this? You can also think about the Hodge bundle as follows. If you look at its symmetric square, sim 2 of E, this turns out to be simply the sheaf of 1 forms over ag bar, the sheaf of 1 forms over ag bar with logarithmic folds. So that's these are some good things about the Hodge bundle over suitable extensions, over suitably chosen compactifications of AG. And you can speak about Hodge classes as well, and you can speak about the resulting tautological rings. So lambda I will be the Chern classes of this extended Hodge bundle, and then we have again an extended tautological ring of AG bar, which is just Q adjoin all the lambda classes, modular relations. So now we arrive at the moment when I have to, I've been very vague about these relations and what they are, but now we arrive at the moment when we can actually specify what the relations are. And the fundamental result here is due to Van der Heer and also to Hainaut and Vivek. They proved the following vanishing result. So the fundamental relation, result here is the fact that the relation, the important relations that you care about are given by the so-called Mumford relation. So, namely, if you look at 1 plus lambda 1 plus ... plus lambda g, and you multiply this by 1 minus lambda 1 plus lambda 2 plus or minus lambda g, the answer is 1. I haven't specified where all these things take place. I've been very vague whether they take place in cohomology or whether they take place in Chow. In fact, it doesn't actually matter for these tautological rings. They're isomorphic if you think of them as Chow's cohomology. So the actual theory doesn't matter. And this relation also holds both in Chow and in cohomology. So let's actually make it let's actually make it hold in Chow of AG bar. So, and this is called the Mumford relation by analogy with MG. So this is called the Mumford relation, and this is due to the fact that it also holds for the moduli of curves, and you can read, and this appears in a paper of Mumford. So the outcome of this is the fact that we can look at the following ring, which will play an important role for us. We can look at the ring Rg, which is simply obtained by looking at Q, adjoining, let's say, G variables x1 ... xg, and quotienting out by the above relation. So quotienting out by the relation 1 plus x1 plus xg, 1 minus x1 plus or minus xg is equal to 1. We can think about this ring, and this ring therefore surjects into the tautological ring of AG bar. So this ring admits a surjection onto the tautological ring of AG bar. And the surjection goes like this. The xi's are simply mapped to the Hodge classes lambda I. So xi, I'm just going to send it to lambda I. So the Mumford relation holds in both in RG and over AG bar. So therefore, you get such a surjective map. So,
sorry, can I ask a question about
yeah,
this?
yeah.
So do you mean this in the graded sense? So do you actually mean these relations, or the ones that you get from these relations is graded? You think of
So each one of these xi's carry a grading. And the grading is the one that you think of. So lambda 1 has rank 1, lambda g has grading g. So this is a collection of relations, in fact. This is a collection of relations. Thank you for the question. All right, so now it's time to introduce the second hero of the talk. I said the talk has two heroes. One of them is AG, and the other one is the guy that will come up next. And this second object of interest is called the Lagrangian Grassmannian, and it appears essentially because of this ring. So maybe a remark, which is the following. We can look at the object LG sub G. So this is the Lagrangian Grassmannian, which is defined as a linear object, linear algebraic object. You start with C to the 2G, you endow it with, let's say, the standard symplectic form omega. And you look at Lagrangian subspaces, so those will be those lambdas in C to the 2G with the property that omega restricted to lambda times lambda is 0, and the dimension of lambda is equal to g. So this is the Lagrangian Grassmannian, and it has dimension g times g plus 1 over 2. So same dimension as AG, actually. And furthermore, not only that it has that dimension, but we can understand, we have a very good understanding of the cohomology of this guy. So maybe, let me say chow. So the chow of LGG, we understand it very well. It's actually our friend RG over there. So this is actually our friend RG over there. And if you ask yourself, how does the Mumford relation appear for the Lagrangian Grassmannian? The answer is very simple. The Mumford relation, which holds in the ring RG, is explained as follows. So the Mumford relation appears on LGG from the exact sequence 0 mapping to S, mapping to O to the power 2G, mapping to Q, mapping to 0. This is the universal sequence of the Lagrangian Grassmannian, and the x's will be the Chern classes of, you have to make some choices. Let me make my choice. The x's could be chosen to be the Chern classes of the dual of the tautological subbundle. So this is the tautological sequence on LGG. So the x's are the Chern classes of the dual of the tautological subbundle, and the Mumford relation is simply the relation that the Chern classes of S times the Chern classes of Q are equal to 1. So this is one such condition. The second condition is the fact that because I am in the Lagrangian case, I can use the symplectic form to identify the dual of S with Q. So S dual is identified with the quotient by means of the symplectic form. So that's why the Mumford relation appears. So in fact, we have all the pieces in place. We have all the notation in place, and it's time to actually state van der Heer's theorem. So here's what he proved. Here's what van der Heer proved. So here's a theorem of his. As I said, from probably 30 years ago. In fact, this map that I defined here is an isomorphism. So the theorem of van der Heer is the fact that, let me state it in two parts. The map from the Chow ring of the Lagrangian Grassmannian onto the tautological ring of AG bar. This map is an isomorphism. So this is the first part of the theorem. The second part of the theorem tells you that if you look at so this involves a compact space, AG bar, but if you care not about the compact space, but rather about the space AG that we started with, in fact, there is only one other relation that you have to worry about, and that relation is, that additional relation is the relation that lambda g is equal to 0 over AG. So we have to impose this other condition, that lambda g is equal to 0. This then becomes an isomorphism with the tautological ring of AG. This is also an isomorphism. And I suppose I should have written xg because that's what I used over there, but everybody understands it. So if you quotient out by the xg is equal to 0, what you get back is this ring R, but in dimension 1 less, for genus 1 less. This is the same thing as Rg minus 1. This is the same thing as Rg minus 1. All right, so in fact, things are even a little bit better than this. We have this explicit understanding of the tautological ring of the moduli space of abelian varieties. It has many wonderful properties, in particular because it's the cohomology of a compact space, such as the Lagrangian Grassmannian. It satisfies Poincare duality, which is a good property to have, I suppose. As I said, things get a little bit better than this, and I would like to elaborate a little bit more on this isomorphism. And explain that, in some sense, we know how to carry out intersection theory of tautological classes in AG bar. So what do I mean by this? Let's start to think about some simple intersection numbers that we can try to compute. And a simple intersection number that we can try to compute will be, we'll try to think about it first on the Lagrangian side and then on the AG bar side. So here's a simple one that we can compute. If I integrate over LGG the class x1 ... xg, I get 1. Why is that? Because xg is essentially Poincare dual of LGG minus 1. That's not hard to see. So xg is the Poincare dual of the smaller Lagrangian Grassmannian, and therefore we can reduce this integral to the Lagrangian Grassmannian where g is replaced by g minus 1, and then you can do this till you actually get down to a single point, and for a single point the integral is clearly equal to 1. So now we can ask what happens on the AG bar side. So of course the element x1, xg, so by the way, this has, I suppose, degree g times g plus 1 over 2 as well, exactly as the dimension requires. So we can actually follow it onto the other side. Onto the other side we get lambda 1 ... lambda g. This is what it maps to. And the question is, do we know how to integrate that particular element? So I can ask, what is the integral over AG bar of lambda 1 ... lambda g? So the answer to this is very explicit. We're going to call this number, it will appear a lot in what follows. We're going to call it gamma sub g. That doesn't seem to be a very good name for it, a very good piece of notation for it in the literature. So let's call it gamma sub g. And this number is very explicit. It's simply the product from k going from 1 all the way to g of the Bernoulli number b to k. So I can look at the Bernoulli number b to k. I can take its absolute values. That's what those bars are. So I can take its absolute values, and I can divide the answer by 4k. So you can ask, how does one get this number? How do Bernoulli numbers appear in this situation? And this is an even older story than the story that I've been reviewing. It goes back to Siegel and Harder. So this calculation, this is due to I suppose first Siegel, and then generalized slightly by Harder. And the way you do this calculation is as follows. I'll just indicate a sketch of the proof just to make it a little bit more believable and see that in fact these numbers don't come out of nowhere. But here's how this is computed. So here's the idea of this calculation. What you want to do is you want to compute the orbifold Euler characteristic of AG bar. So let's try to do that. So we'll try to compute the orbifold Euler characteristic of AG, sorry, not of AG bar. So we want to compute this orbifold Euler characteristic. In fact, in order to compute it, all we have to do is to apply the Gauss-Bonnet theorem. So to compute it, we apply the Gauss-Bonnet theorem. This is the integral over AG bar of the top Chern class of the sheaf of logarithmic differentials, so of omega AG bar log. And because I'm thinking about cotangent things, I have to actually change the signs as well. So there is a sign issue here. So -1 to the dimension g times g plus 1 over 2. This is the sign issue that needs to correct the integral. But now, if we remember what was on this board, this sheaf of logarithmic differentials is connected to the Hodge bundle. There was a third item that was written on the board before that essentially explained us how to think about the sheaf of the sheaf of these logarithmic differentials. And instead of this, I can replace it by sim2 of e. So this can get replaced by sim2 of e, the second symmetric square of the Hodge bundle.
Just ask quickly, why?
Yeah.
You see Gauss-Bonnet, why is it the log differentials instead of just the differentials?
Because I'm actually computing the orbifold thing of AG.
Oh, okay.
So I'm throwing away all the open stuff, and as I throw away all the open stuff, they contribute, and the contributions add up so nicely that you get exactly the sheaf of the relative differentials. So now, since I'm looking at sim2 of e, I can express that in terms of the Hodge classes, and using a little bit of combinatorics and the Mumford relation at the next step. So Mumford and the Mumford relation at the next step. This yields 2 to the g times lambda 1 lambda g integrated over AG bar. And then there is the sign that I have to carry around -1 to the power g times g plus 1 over 2. So that's one way of computing this orbifold Euler characteristic in terms of the Hodge classes. The other way is the calculation which is due to Siegel and Harder, which tells us exactly what this value is, and they did the calculation slightly in a different way by integrating certain metrics and computing various volumes. But what they found is the fact that this is exactly the constant that's written there. So up to this 2 to the g times the sign, they find exactly the answer that we claim. So we can actually extract this integral of lambda 1 lambda g over AG bar from their work. So now, in fact, not that I'm aware. I'm not aware of an algebraic geometry proof of this, but yeah. Yeah, I will get to that. Yes, that we'll get to that. All right, so let me now state a more general result. So this is called the Hirzebruch-Mumford proportionality. So Hirzebruch-Mumford principle. So we'll abbreviate this HM, proportionality. So Hirzebruch-Mumford proportionality is a general result, is a much more general result, but in the case of AG, it takes a very nice and simple form, and it's also very easy to prove in our case. It simply tells us that if you want to integrate any polynomial over AG bar in the tautological classes, if you want to compute lambda 1 to some power A1, lambda G to some power AG, in fact, you can, provided that you know the intersection theory of the Lagrangian-Grassmannian. This is always going to be almost the same as the intersection numbers over the Lagrangian-Grassmannian of the similar polynomial in the x's. So x1 to the a1, dot, 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 xg to the ag. So integrate the similar polynomial in the x's. But of course, this cannot possibly be true, because even when I make this choice, x1 dot, dot, dot to xg, I'm not going to get a true equality, so I have to modify everything. All of these integrals are proportional to each other, and the proportionality constant is exactly this, this number, gamma g. So that's in some sense a full description of the intersection theory of tautological classes over AG bar. It tells you that if you want to integrate any such class, it's enough to actually do it over the compact dual, over the Lagrangian-Grassmannian, and multiply by this number, gamma g. The proof of this result is also very simple, actually. The proof of this result, I'm going to say it in words, I'm not going to write anything down on the board. Because we're computing intersections in isomorphic rings, and because these rings, the top degree part is one-dimensional and it's spanned by x1 dot 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 xg, it means that when I do this calculation, I'm going to get a multiple mu of lambda 1, lambda g. So some of these a's will be 0. And here, when I do the calculation, I'm also getting a multiple of x1, xg for the top degree part. And because the rings are isomorphic, the same multiple works. So the same mu appears on both sides because the two rings are isomorphic. And therefore, these two calculations that I presented essentially prove the Hirzebruch-Mumford proportionality principle for AG bar. So that's the half of my talk. I said that actually half of my talk will be spent reviewing all the results of Van der Heer, which are absolutely necessary to actually paint the picture that our understanding of AG, of the tautological ring of AG, is actually pretty good. So now I'm going to go to the second part of my talk, in which I have to tell you some newer things. So maybe for the second part, let me begin with a first result. Let me begin with the first result we can prove, and this result has to deal with the Hodge class. So this is the result that I proved with Sam, and Rahul, CMOP. And the result says that lambda g is equal to 0 on the boundary of any toroidal compactification of AG. So you pick any toroidal compactification of AG, you look at this boundary, and the class lambda g is actually equal to 0 there. So this is kind of a funny state of affairs for the following reason. It's kind of a funny state of affair for the following reasons. First of all, lambda g, if you remember my description of the tautological ring of AG, lambda g was equal to 0 in the interior on the moduli space AG. So this is 0 on AG. It's also 0 on the boundary, so lambda g is equal to 0 on the boundary. However, lambda g is not equal to 0 over the entire moduli space because it evaluates to this funny combination of Bernoulli numbers. So lambda g is not equal to 0 AG bar. So this is a very tricky class from that point of view, right? It tries very hard to be 0, and it does so in little pieces. So is this a result that perhaps was expected or not? Was it known to people before or not? In some sense, So we communicated, when we're thinking about these issues, we communicated with Van der Heer, and he gave us an argument in characteristic P. And his argument is very nice and very easy. So maybe I can say something about the characteristic P argument.
Does this hold on MG?
Yeah, this holds on mg bar, and the reason for which it holds on mg bar is because there is the Torelli map, which is defined on mg bar, and lands in a certain compactification of AG, namely the second Voronoi. And there you can pull it back by the second Voronoi. But this was also known on mg bar before this argument. So this actually, you can find this in paper of Faber and Pandharipande over mg bar and AG being replaced by mg compact type. So that's kind of that's how it goes there. So so you can actually recover those results from if you know the Torelli map extends. So the characteristic P argument is pretty fast to describe, and this is due to Van der Heer, as I said. The characteristic P argument is easy to describe, and essentially Van der Heer says in the locus of so when you think about AG bar and characteristic P, think about the locus of those let's say semi-abelian schemes for which the P rank is equal to 0. So Van der Heer calculated the class of this locus where the P rank is equal to 0, and he found it's actually a multiple of lambda g. It's a very explicit multiple of lambda g. He knows exactly what it is. But now, when you start thinking about degenerations of abelian varieties, over the boundary, the P rank will start to jump. So the P rank locus is equal to 0 turns out to be a compact subvariety of AG. This is a result of Word. And therefore, when you restrict it to the boundary, it disappears, it vanishes. So that tells you that lambda g is equal to 0 there as well. So in fact, something stronger happens. So in fact, we can prove, so in all characteristic over C, let's say, in fact, you get even more vanishings of lambda classes. In fact, we can prove that if you look at lambda g, this is 0 on the boundary, but lambda g minus 1 is also 0, and lambda g minus n plus 1 is also 0. But that's if you look in the correct places in the boundary. So maybe, so this holds in the Chow ring of AG bar at least equal to M. So what does that mean, AG bar at least equal to M? That actually means that you look at those degenerations of abelian varieties for which the torus rank is at least equal to M. So you get in the semi-abelian part, you get higher and higher, tori. So that's good. That's the first result. Yeah. So I think that I said something about the proof when I spoke about characteristic 0 or characteristic P in some sense. And if you want to speak about characteristic 0, essentially the idea is to construct sufficiently many co-sections of the Hodge bundle. And depending on how deep you are in the moduli space, you construct more and more of these co-sections, essentially. How do you construct them? You essentially have to think about logarithmic differentials, these guys. Those are what give you the Hodge bundle, and take residues of these logarithmic differentials along the singular loci. And that's as much as I want to say about the proof. All right. So now I still haven't defined the tautological projection, so maybe I'll do that next. So here's the second result. Here's the second result that I would like to explain. So theorem. There exists a diagram which is commutative. And the diagram goes like this. I start with the Chow ring of AG bar. I can compare it by restriction with the Chow ring of AG. So this is a restriction. And then I can ask, well, how can I compare those with the analogous tautological rings? So I have R star AG bar here, and I also have R star of AG here. And there are natural maps like this. So now, because I said there exists a commutative diagram, I should probably tell you how to complete the diagram. So the completion of the diagram involves arrows in this direction, which will be called proj for projection. So now, what's the contents of this theorem? How should you think about this? I'm claiming that the first arrow is easy, and the second arrow, so this is kind of the key of this theorem. The first arrow is very easy. The second arrow is essentially, it essentially follows from the previous theorem, and it uses the previous theorem. So this is using lambda G vanishing. So let me give some details. The details are a little bit linear algebraic, so there's going to be a little bit of linear algebra in what follows, but let me actually start by explaining the top arrow. So the top arrow, it's not very hard to explain actually. You can look at the Chow ring in degree k of AG bar. You can pair it with the tautological ring in degree G plus 1 over 2 minus k of AG bar. You can land in the Chow ring of degree G plus 1 over 2 of AG bar. And then we can integrate to get to a rational number at the end. So we can follow this, this intersection pairing followed by integration, and then we get all the way down to Q. But now, if you remember, the tautological ring of AG bar satisfies Poincare duality. So when restricted to RK of AG bar times the same things, this is perfect. So in other words, what this means is the following thing. It means that actually if you fix any class alpha in the Chow of AG bar, and if you look at the functional beta mapping to the integral of alpha times beta over AG bar, and you allow beta to be a tautological class, so beta is a tautological class, so you vary beta in the tautological ring. This functional, because it's a functional on the tautological ring, so this is a functional on the tautological ring, on R star of AG bar, and this ring satisfies Poincare duality, it must be given by pairing with a tautological class. So this must be given by pairing with a tautological class, which we're going to call the projection of alpha. So to every single cycle on AG bar, I can find a tautological class proj alpha. So this guy is tautological now. For every single class on AG bar, I can find a tautological projection proj alpha with the property that alpha and proj alpha have exactly the same intersections with all complementary tautological classes. So in other words, I can write alpha to be a tautological part plus, which I call projection, plus a purely non-tautological part. And this purely non-tautological part intersects every other tautological part, or every other tautological class in 0 after integration. So this n-taut part, pair it with any beta, you integrate, you get 0 all the time. So now that's how we explain, that's pretty easy. So that's pretty easy. This is how we explain the top arrow. The bottom arrow is pretty much the same, in fact, but it involves only one twist. So let me explain that one twist. So it explains only one twist. It involves only one twist. And the twist is due to the fact that this tautological ring has an extra relation given by lambda g is equal to 0. So we have to actually take that relation into account and carry it along and make sure that in fact things behave well. So for the bottom arrow, here's how the argument might go. So for the bottom arrow, here's how the argument might go. We're going to do exactly the same things that we've done for the compact part, except some numerics will change. So I can look at CHK of AG. The so-called in the tautological ring forces me to change dimensions, so I can look at CHG times G minus 1 over 2 minus K. Actually, I said R. Sorry for this. R of G minus 1 over 2 minus K of AG. Why the change in dimension? Before it was G plus 1 over 2, now it's G minus 1 over 2. Why the change in dimension? Remember that when we spoke about the non-compact space, I had to change G into G minus 1 in Van der Heer's theorem, so that's dictated by that. This lands in the tautological ring of G minus 1 over 2 of AG. This lands in, in the Chow ring of AG in dimension G times G minus 1 over 2. And then the crucial part is that this then can be promoted to a class in G times G plus 1 over 2 of AG bar by multiplication by lambda G. And then we can go ahead and integrate, and we land in Q. So the bottom arrow is pretty much exactly the same procedure as the top arrow. The only new thing, the only new feature is this multiplication map by lambda G. This is the only new feature. And in order for this map to be well defined, how does this map go? This map will go start with alpha on AG, and you want to produce a class on AG bar. So the way it will go, it will be like take alpha, extend it in any way you want on AG bar. An extension will exist, because the map in Chow is surjective. Take alpha, extend it in any way you want, you get alpha bar, and then you multiply it by lambda G. And now you might be worried that, in fact, this might depend on the extension that you picked. Maybe it depends on the way you picked alpha bar. But in fact, this is not the case, because any two extensions differ by boundaries. A lambda G essentially kills everything that's on the boundary. So for this is well defined, because lambda G is 0 on the boundary of AG bar. So any two extensions will differ by stuff on the boundary. So lambda G will kill this ambiguity. And then you run exactly the same linear algebra as before to get this decomposition. So the upshot of this is that even for cycles on AG, so this should hold even for cycles on AG, you should have such a decomposition of a cycle on AG into a part which belongs to the Van der Heer ring, and a part which in some sense is orthogonal to the Van der Heer ring, but orthogonal means orthogonal after you pass through compactification, multiply by lambda G. So maybe in the last 10 minutes of my talk, I should probably give you some concrete examples of how this projection works. Just because you defined it, it doesn't mean that you can compute it. So I would like to actually show you some very concrete calculations of these tautological projections.
I mean, is it obvious that it does not depend on the complexity?
Yeah, that's a good question, and the answer is obvious, that at the end of the day, the actual decomposition doesn't depend on the compactification, because you start with 2 and you dominate it by a third, and you have to follow it along. So it's not too bad. So let me give you some concrete examples of tautological projections, and probably the simplest geometric cycle one can think about in the moduli space of abelian varieties is a product of lower dimensional moduli spaces. You can look at AG1 times AG2 ... times AGL, where G is equal to G1 plus ... plus GL. And so this, you can look at this locus that maps to AG. So this locus that maps to AG, and essentially the way it does is you pick L abelian, principally polarized abelian varieties of dimensions G1, G2, and GL, and you take their product together with the product polarization, and therefore you land in AG. And then what you can do is you can push forward the fundamental class of this to get a cycle in AG, and you can ask, what is its decomposition into tautological and non-tautological part? So the theorem will tell us what it is. So the tautological part of AG1 times AGL. So the theorem will tell us what it is. And essentially, the answer is, it's a very simple answer. It's actually it's remarkably easy to actually compute the tautological projection of this loci. And the answer is as follows. You're going to look at a prefactor which involves these Bernoulli numbers. So we're going to have gamma G, which is this funny product of Bernoulli numbers, and it will appear in genus G, and it will also appear in genus G1 ... GL. So that will give you some Bernoulli numbers. And then the other thing that will appear in the formula is also fairly easy. There will be a Schur determinant. So the answer will involve a Schur determinant. So I'll have to write it down. And the Schur determinant involves lambda classes. So there's going to be some lambda classes that I have to populate this determinant with. And they have to be, I have to tell you what indices these lambda classes have. And the indices are determined by a partition. So I have to tell you a partition alpha. And I'll tell you all of these things in a second. So lambda classes will be, there'll be an explicit partition. Let me write it now. So alpha is the explicit partition G minus G1, G minus G1. This appears G1 times G minus G1 minus G2. This appears G2 times, it appears repeated itself, G2 times. And then you continue all the way till the end. So start subtracting G minus G1 minus G3, that will appear G3 times, and all the way at the end, G minus G1 minus GL, that will appear GL times. This is also known as the number 0, because all the G's add up to big G. So that's a partition, it's a very explicit partition. And this partition is used to give me indices for the Hodge classes. So lambda, on the first row, I will put lambda corresponding to the index alpha 1. So in my partition, I have to look what happens on the alpha 1 position. Alpha lambda 2, lambda alpha 2, lambda alpha G. So this is a G by G determinant. And then I have to increase the indices along the rows. So lambda alpha 1 plus 1 here, lambda alpha 1 plus G minus 1. And here lambda alpha 2 minus 1, and here lambda alpha 2 plus G minus 2, I suppose, and so on. So the rows have increasing indices by 1. So that's a pretty easy formula, and that's a pretty easy formula that appears in this case.
What's the size of this partition?
Sorry?
What's the size of this partition?
Yeah, so this partition will have G1 plus G2 plus GL. G, exactly G.
That's the sum of all the...
No, the sum, I don't know off the top of my head, like what the sum of all the entries are. So it's probably going to be some, like if I am to guess, I think it's sum of GI times GJ, something like that. So you have to look at all those things. Sorry?
These sort of degeneracy loci were actually some sections.
Yeah. I have 5 minutes, so I have to say so, to make some choices as to what I'm going to say. So how do you prove this? So how do you prove this? The way you prove this is as follows. You have, in order to prove a theorem like this, you have to actually pass through the compactification of AG. So you have to pick your correct compactification, and you also need to be able to close the class alpha to take this closure. You have not only that you have to pass through compactification, but you have to be able to close up all the product loci. So the correct compactification to do so is the perfect cone compactification. The fundamental thing about the perfect cone compactification is that and this is a result of Nick-Shepard-Barron, is the fact that if you close up this locus, then it becomes this, the closure of the individual locus, loci. So this holds over the perfect cone in such a fashion that it's compatible with the Hodge bundle as well. Now, this determinant, the determinant that appears on the other side, arises from the Lagrangian geometry. It's born in Schubert calculus. And on the Lagrangian geometry, you can solve an analogous problem, namely the problem of finding the class of the product locus inside of LGG. And this is done, this is done using Schubert calculus and techniques of this form. The constant that appears here is essentially the translation between abelian varieties and Lagrangians, done judiciously. You have to actually follow everything around and to identify this factor. So this is a reflection of Hirzebruch-Mumford, and this is the reflection of Lagrangian geometry. And if you put things together correctly, you get exactly this tautological formula, provided that you pick your suitable compactification. I see that I have 2 minutes and 4 seconds, so maybe I can write down 1 or 2 formulas concretely just to see how they look like. So some examples. So these determinants are pretty easy to compute in general. So if you want to look at the tautological projection of A1 times AG minus 1, you're going to get something like G over 6 times the absolute value of the Bernoulli number times lambda G minus 1. But here's another one you can do if you want to look at the tautological projection of A1 times dot 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 times A1. You're going to find that this is equal to product of K over 6 absolute value of Bernoulli 2K, K going from 1 to G of lambda 1, lambda G minus 1. That's, there are many other formulas you can write down. Essentially, it's a matter of computing, doing some linear algebra. But of course, this leaves us with the following question. We know what the tautological part of these product cycles are. How about the non-tautological parts? Are they 0 or are they not? I think this is a very interesting question to figure out what the complementary non-tautological classes are to detect whether they are 0 or not. It's likely to be a very hard question. You're not going to be able to solve it numerically because by their very definition, the non-tautological classes pair trivially with everything else that's tautological. So by their very definition, whatever's left to make up the cycle A1 times AG minus 1 is going to be a class that, it intersects everybody else in 0. Everybody else is tautological in 0. So to find it, you have to do something else. So I'm going to stop here. I finished exactly at 0, 0, 0.
Wow, perfect, amazing. Are there any questions? Yeah, Jennifer.
So is there any, in these geometric examples, is there any cases that it's known to be non-tautological?
Yeah, so I can comment on this. Let me be positive at first. So when G is at most equal to 3, everything is tautological by all the results of van der Heer, essentially. So the most interesting cases are starting at G is equal to 4. In G is equal to 4, I don't know of a non-tautological example. In fact, I don't think there exists one. So I think that in G is equal to 4, conjecturally, I would say that all the product cycles are tautological. I have no speculation in when G is equal to 5. I can go one way or the other. I have no idea. The only thing that I know is in genus equal to 6, we know that A1 times A5 is not tautological on A6. And this is work that I did with Sam Canning and Rahul, and we managed to prove that A1 times A5 is not tautological on A6, and we did hard work to actually prove this. This is a very difficult class to understand. But I suspect that essentially you know, most of these guys are not going to be tautological. They don't look tautological, so why would they be? So in general, I suspect that most of these guys will not be. Yeah.
Is that are you making these statements in cohomology or in Chow?
I'm making these statements in Chow.
So in cohomology, do you know any non-tautological classes at all?
This is like the cohomology in Chow of AG is a complete mystery. Like, I think that the results that we have, essentially we have a good understanding up to genus 3, some understanding in genus 4, and then.
So there's this interesting phenomenon that AG has this, the tautological ring has this so-called in lower degree. So is it conceivable that AG deformation retracts onto a compact manifold of lower dimension?
I mean, I don't know what compact manifold that would be.
You see what I'm saying?
But yeah, I understand, yeah. I mean, in some sense, Lagrangian Grassmannian kind of plays this role of the surrogate, right? That's kind of, the compact dual has this, you know, this other role of inducing Poincare duality, right? Yeah.
But in this, in the genus 6 example, doesn't the proof reduce to the moduli space of compact?
Yeah, it does, yeah, you know this.
Yeah, I mean, somehow, I think there it is in cohomology. I mean, somehow, I think the tautological ring on the abelian bar is yes, that's also not tautological.
Alice, you had a question, did you?
Yeah, actually, just following on from Michael's. So, is there a geometric relationship between AG and or AG bar and this LGG? I mean, it looks like there could be some kind of multi-valued correspondence. Actually,
no,
so
it's more like on the
left-hand side equals right-hand side because we compute this and you compute that, and it comes to the same thing. But is there any geometric?
So
thing?
you know, there is a general principle, right, about where this applies. I'm not an expert in this, and. But LGG is called a compact dual, and essentially it happens all at the level of the Siegel spaces that you can define the so-called Harishchandra embeddings into compact duals and so on.
But that would be AG and not AG bar.
No, that would be AG before even taking the quotients. Yeah, so it's not a very well defined. No, there's no geometry behind it other than what I said.
Any other questions from online?
Not we can have lunch.
Yeah, okay, so let's thank Dragos again.